Hi, in this session, I'm going to talk to you about comparative analysis. I'll begin by exploring data and then making our way into inferential statistics using some comparative analysis methods. Just to set the stage where we are, in the research process, you typically go and gather your data based on a research design. You then prep or organize or clean the data. Once that is done, the next step is to conduct some analysis of the data. First, you'll attempt to describe the data by examining some descriptive statistics. Thereafter, you'll conduct some level of inferential statistics to draw comparisons and draw inferences about the population based on the sample. So I'm going to begin here by looking over how to summarize your data, specifically examine descriptive statistics, and then make our way into inferential statistics, which is going to involve comparing variables, comparing a variable to a threshold, and comparing groups of a variable. So here's what we're going to be doing. Let's begin by looking at how to summarize our data. The act of summarizing our data involves describing the data, hence called descriptive statistics. Amongst these, you can examine a frequency distribution. The frequency distribution is a distribution of frequency counts for different levels of a variable. For a metric or continuous variable, you typically bin the variable to make it discrete, and then examine frequencies of the various bins of the continuous or metric variable. And that gives us a frequency distribution. When you express that as a graph, it's called a histogram. We'll then examine measures of central tendency, specifically mean, median, and mode. We typically look at multiple measures of central tendency because each one of them is susceptible to different sets of biases. The mean is the most widely used measure of central tendency. However, it has been known to be susceptible to outliers. An outlier can drag the mean higher or lower. On the other hand, the median may not be the statistical middle of the data. However, it is less susceptible to outliers. The mode similarly looks at the most frequently occurring observation and is less susceptible to outliers than is the mean. So a discrepancy between the mean and the median and mode would then signal that you may have outliers at work. Similarly, when examining the spread of the data, we examine multiple measures of dispersion. These tell us how spread apart the data is. Is it tightly crunched together, or is it spread over a larger range of data? Range specifically refers to the difference between the minimum and the maximum for the data. The interquartile range represents the distance between the 25th percentile and 75th percentile. That is the middle half of the data. The standard deviation and variance are related as being square root and square. The standard deviation is a standardized measure of deviations of each observation from the mean. The coefficient of variation similarly is derived from the standard deviation. Generally speaking, larger values would indicate more spread or more dispersion in the data. Then we get to measures of shape. There are two widely used measures of shape, skewness and kurtosis. Skewness refers to whether the tails of the distribution are equal, or is a tail longer on one end than the other one. If it is unequal, the tails are unequal, you'd say the data is skewed either left or right. Kurtosis refers to how peaked the data is or how flat the data is, specifically how flat the distribution is. To give context, as we go through these slides, my goal here is to demonstrate each of the analyses as we go through. To provide some context, this is based on a survey of 2,000 respondents that I'm going to pull up for you in just a second here. Here's a survey that was then shared with 2,000 respondents, asking them about their health consciousness. And we have here 3 measures of health concern that they would score on a scale of 1 to 7, like this. And then they would also rate 3 popular fast food restaurants in America. They could either rank order them, or they could express this using Likert scales. And eventually they would share their information about their gender, and they would then hit the submit button. Okay. That eventually gave us a data set of 2,000 respondents. They were noticing data, the data was complete, and we prepared and cleaned the data in a previous session. Let's move on to examine how you would look at descriptive statistics for this data. So we're going to go and examine here to get started, to begin with, examine a frequency distribution, measures of central tendency, dispersion, and shape for the rating of McDonald's. To do so, I'm going to switch screens and go to the fastfoodcoded.sav file. This contains the data file from the survey that was imported into Spss and then cleaned and organized. This is what it looks like right now after being prepped and cleaned. Just without the value labels, this width. Now, of interest to us here is the variable McDonald's. We want to examine a whole bunch of descriptives about McDonald's. The rating of McDonald's was gathered on a 1 to 7 scale, where 1 is strongly disagree and 7 is strongly agree. Or I think 7 is a high scale indicating a lot of liking for McDonald's, and 1 reflecting a dislike for McDonald's. The scale is such, it's a this is a interval scale variable. So what we're going to do here is we're going to now conduct some descriptives out here. To do that, I'll go to Analyze, Descriptive Statistics, Frequencies. From here, I'm going to select a whole bunch. I'm going to select variable McDonald's and move it over to the right. Next, I'm going to check a few boxes here to indicate the descriptors we are interested in. Mean, median, mode, standard deviation, variance, range, min, max. Lastly, I'll also check boxes for skewness and kurtosis. Next, I'll request a chart for the histogram and normal curve and histogram. This will construct for us a frequency distribution. For most metric variables, you would have to typically construct the bins. In our specific case, the variable is already binned in a sense, because we have 7 levels for the McDonald's variable. You could either mark McDonald's being a 1, 2, 3, so on to 7. Therefore, it's already binned. Now, notice it says display frequency tables out here. The box is already checked, which means by default, Spss is going to run frequency tables for this variable. Given that we only have 7 levels, it's okay to leave that box checked, even though we're working with a metric variable. On running that, that bit of output, that instruction, we are going to get our output in an output window, which looks like this. Let's go over the numbers we've gotten from this process. So our mean is 3.49. We have a median of 3. This is telling me we might have some outliers here, or we might have an outlier. It's worth mentioning here, if the mean and median are identical, that doesn't mean you don't have outliers. It simply means you may have no outliers, or you could have outliers that balance each other out on either side of the scale. But this is telling me that we have an outlier on the higher end. There's some numbers that are kind of on the higher end that are outliers in our data. We'll get a better sense of this when we look at the distribution of the data. The standard deviation variance are not as useful alone, individually, in isolation. They're more useful when you can you look at these numbers for other variables, like in our case, Chipotle and Shake Shack. We also have information here about the skewness and kurtosis. Skewness is telling us that the data is not skewed at all. It's pretty close to 0. And kurtosis is not very large either. So we have indications here that the data is fairly balanced. Our data is covering the full range of the scale from 1 to 7. Moving along, you can look at the frequency distribution here from our table. So you can see out here that we have a little bit of a drop here in the middle, or there are a few people sitting on the fence for McDonald's. There are people who like it, people who don't like it, but not as many people in the middle. Also, you're noticing the upper end is lighter than the lower end of the scale. Hopefully you can notice here, there's some big numbers on top and small numbers on the bottom. Smaller numbers on the bottom. Let's look at the frequency distribution here to get a better sense of this. So we're seeing the same thing here, that the large majority of people are not liking McDonald's as much. So not so finger licking good. And on the high end, we're seeing of the scale, we're seeing not as many people checking those boxes. Okay, so that's how you could examine the descriptive statistics for, let's say, a variable like McDonald's in this case. Now, there are times when you want to examine descriptives, but for different groups. There are a couple of ways of going about this. One is you can examine descriptives for one group first and the other group later. Like set up a filter for males and examine descriptives for McDonald's for males. Then repeat the same for females. An alternative method is to compare them both in the same exact table. This latter method is what we are going to examine now. Going back over to Spss, we'll go to Analyze, and I'm going to go over to Descriptive Statistics and go into Explore. Here, we get a little window popping up where we can specify a variable to compare the groups on. So looking at McDonald's here, and just for, let's just add two more variables just for the heck of it. Okay, so I'm moving in Chipotle and Shake Shack also, so we get some more context. We're comparing all of these across the genders, male and female. Now, there are a couple of statistics we can check or select from this, but as we can see out here, descriptives are already selected. So I'll leave that as it is, not worry about that. Having done that, I'm going to go and hit OK, which is going to give us a display containing both statistics and plots. Okay. Having done this, let me now switch over to the output window so you can see what happened from running that analysis. Here's what we got. So now notice I've got some more nuance here. You also got Chipotle and Shake Shack in addition to McDonald's. We can see out here that there are more females in our data set than males. And let's go to the key variable of interest, which is McDonald's. So we want to see out here how our two genders differed on the variable of interest. So here we are. You can see out here that for males, the average is a little lower than for females, but really the difference is seems marginal. You look at the median, the numbers are exactly the same. The variance, not much different, 3.87 to 3.979. All in all, it seems like whether you look at men or women, they feel pretty much the same about McDonald's. We can do a similar comparison for Chipotle and Shake Shack as well. And then you've got these box plots that show you again a distribution of males, females, and you can see these box plots are telling a story. The box plot is set up so that one half of the data lies in the box. That is, the extremities of the box in the box plot represent the 25th and 75th percentile of your data. And you can tell by looking at this that, the median is exactly the same. The median is that dark line you see in the middle. And so the distributions of these two variables, of these two groups on McDonald's, are pretty much the same. A box plot is a commonly used tool to compare variances or variation in variables or groups across a variable. Okay. And then we have data on the other two variables I also got data on, which is Chipotle and Shake Shack. All right, so that was one way you can examine descriptive statistics. Now, having looked at the data on McDonald's, you might look at that and say, well, the mean wasn't exactly the same for males and females. In fact, that is true. The mean for males was slightly lower than that for females for McDonald's. And then you got to wonder, well, is that difference, big enough, or is that, large enough? Let me go back to that output window to put this in context then. As you look at the numbers in the slide, in this output window, you look at the numbers for males. The average is 3.45 for McDonald's. And for females, 3.52. In this sample, females love McDonald's more than males, right? Because in the sample of 2,000 respondents, the average for females is higher than that for males. We're usually interested not only in knowing how our sample feels about the issue at hand, but also how the larger population they represent feels about the issue. So the main purpose of doing a survey then on a sample of respondents is to learn about how the population feels. The sample is designed to represent the population. It is not the population itself. The question then is, well, is 3.45 small enough compared to 3.52? Or can we say the numbers are so close together that the differences are not statistically significant? I may have jumped the gun there by talking about statistical significance. So let's get right to it. When you take a sample and extrapolate to a population, you're engaging in inferential statistics. The machinery of inferential statistics relies on a procedure of hypothesis testing. Let's pay tribute to that first. Let's talk about statistics. So in the world of hypothesis testing, we typically formulate a pair of hypotheses, HO and H1. They are set up so that HO and H1 cover the universe of possibilities. If it's not HO, it must be H1. It cannot be anything else but those two things. And both cannot be satisfied at the same time. So they're collectively exhaustive and mutually exclusive. Next, you select an appropriate test. Choose whether there's a t-test, a chi-square test, an f-test, so on. You choose a level of significance, a decision of at what threshold would you reject the null hypothesis. That level of significance is called an alpha level. Typically, we say the alpha is a 0.05, but it doesn't have to be. It could be a 0.1. And if you feel you want to be very conservative about your test, you could drop it down to 0.01. But whatever the choice of alpha, once decided, it should not be changed during the study. Next, you go on and gather data and calculate that test statistic. Based on that test statistic and based on data gathered, you compute the test statistic. You might come up with a value for the t statistics, if that's the appropriate test chosen, or the f statistic. You then determine the probability associated with that test statistic. What p-value does that, t-statistic translate to? You then go on to compare that p-value to an alpha value. If the p-value is less than alpha, then you reject the null hypothesis. Right? So usually if p is less than alpha, you will reject. And then you'll draw some conclusion. Let's examine this through the lens of an example. So here we have our first step. We have the hypothesis set up. We have a pair of them at a restaurant. We're saying the tip is $2.50 or it's not $2.50. As you can see, the two hypotheses are mutually exclusive and collectively exhaustive. The tip must be, equal to 250 or not. It cannot be in the middle, and the two cover all possibilities. The next step is to figure out a test statistic. Now, as far as the machinery of hypothesis testing is concerned, here's what we're going to be doing in a nutshell. We're going to run through some test statistic or decide our test statistic. We'll set an alpha value. Let's say that alpha value is 0.05. For convenience sake, let's just stick with the traditional norm of 0.05 alpha level. And then we'll gather some data. That data will then tell us, based on the data gathered, we're going to get a statistic. Let's say a t-statistic. From the t-statistic, we'll figure out the p-value or probability value. Let's say that p turns out to be 0.04. Okay, so here's what it means. It means that we're assuming the null hypothesis to be true. That's our base assumption. Until we reject or until we have overwhelming evidence the null hypothesis is not true, we're not going to reject it. So let's see what that means based on our data here. So we've gotten a p-value of 0.04. What it means is that that if, in fact, the null hypothesis were true, if this were true, the p-value is telling us the probability of getting the data we got is 4%. Again, to be clear, the hypothesis process is telling us that if the null hypothesis were in fact true, the probability of getting the data we got is a mere 0.04 or 4%. Now you'd say, well, wow, that's a pretty low chance of getting the data we got if the null hypothesis is true. Well, it is in fact low, but how low is it? Well, 0.04 is lower than our threshold of 0.05. So it's pretty low then. So given that the probability of getting this data is so low, is telling me maybe this null hypothesis is not right to begin with, because we know what data we've gotten. The data we know, let's say, is collected through some genuine methods, and there's no errors out there, and has been gathered reliably. So we've gotten the data we got. Therefore, maybe a null hypothesis is not true. Therefore, it should be rejected. If it's rejected, we're going to go with the alternative H1, which indicates that tip is not equal to $2.50. Okay. Which means it could be either more than 250 or less than 250. This may not be a practically useful result. A restaurant manager might want to know if the tip is less than or more than, not necessarily knowing simply that it's not 250, but it's more than or less than maybe a trivial solution to the restaurant manager. This is sort of like what happens when you get to run a two-sided or two-tailed test. Later on, we can examine a one-tailed test, which might be more practically useful than a two-tailed test. Okay, let's walk through some more slides on how this process unfolds then. So the tip is 250 is our null hypothesis. If you were to examine a frequency distribution of data gathered, here's what it would look like. And if you were to draw a frequency polygon on top of that, it would look like this. And here is the distribution of the data. As you can tell from looking at this picture, there were some people who paid a lot in tip, as much as $10, and there were a few people who paid nothing for a tip. But most people paid something around this number, these numbers here. Now, our null hypothesis is this, that the tip is $2.50. Having made this null hypothesis, we now go and test the hypothesis. We do so by collecting some data. When we gather some data, we find out that our hypothesis is, averages $3 or so. Now, our HO is 250. Our data is telling us that the average is $3. That is, in the sample, the average tip is $3. They're obviously at odds in the sample. They're obviously different in the sample. What we really want to know is this number pretty far out from 250? Well, so one way we could examine this is by constructing a confidence band that looks like this. These confidence bands show us, well, what is the 95% confidence interval around 250? That is, if in fact the null hypothesis is true, what kinds of numbers should you see for a random sample? It's saying that for a random sample you draw, if this were true, 250 were true, any sample average you get should be in that light blue lines band, the 95% confidence band then for an average of 250. Clearly, the sample data we have gotten is way out of the 95% confidence interval. The question then is, well, how far out is it? Can we compute a probability? Well, if the null hypothesis were true, what is the probability of getting the data we've gotten? Well, that number is called the p-value. In our case, that p-value happens to be really, really low. And so what you would typically do is you'd say you find out p is less than alpha, and that would then lead you to reject the null hypothesis. Once you reject the null hypothesis, you must rule in favor of the alternative hypothesis. Hopefully that process was clear enough. We're going to be following the same exact methodology to examine a whole bunch of inferential statistics. The test might change, but the hypothesis machinery is pretty much the same. Ideally speaking, you must state the hypothesis before you conduct the test. In practice, many times people will have a mental idea of what hypothesis they're running, but they may not explicitly state it. But bear in mind, more than likely, there is a hypothesis that exists, even if not explicitly stated by the authors. Now, there is a whole kind of group of researchers who believe in sort of like, why don't you just do a data mining kind of process out here? And they would, vote in favor of skipping the hypothesis part. In fact, there's arguments being made in terms of how I can hack the p-value. Basically, setting hypotheses helps us keep the process honest. Okay, and so that's something a little bit of a segue. If you want to pursue this, you can take a look at. We're going to now look at how you can conduct comparative analysis. So in the next couple of minutes, I'm going to go over a couple of different kinds of analysis you can conduct, one after the other one. There are three broad kinds of tests we're going to conduct out here. that exists in two different families. On the left is a family of parametric tests, on the right, the family of non-parametric tests. The family of tests on the left assume some knowledge about the distribution of the data. The ones on the right don't make any assumptions about the distribution of the data. The ones on the left typically involve variables that are metric in nature, interval or ratio scale data. The ones on the right typically involve rank order data. So long story short, when you're working with parametric tests, you have more flexibility, more leeway to conduct and examine tests. With non-parametric analysis or tests, there are limits in terms of what you can do with the data. Simply put, something as basic as conducting a mean is not viable if your data is rank order. And so you got to find out roundabout ways of conducting statistical or inferential tests. Our focus here will be on parametric tests. I will not be reviewing non-parametric tests in any detail at all. So focusing here on parametric tests, we have three kinds of tests in this category: a one sample test, independent samples test, and a paired samples test. And those are three tests I'll focus on through a couple of examples. Okay, our first test involves comparing a variable to a threshold. There are often instances when you have a data set that looks something like this. In this toy data set, you have four variables, A, B, C, and D. For now, I'm going to focus only on C. C contains a bunch of numbers that seem to be interval or ratio scaled, otherwise metric. There are times when you want to look at a variable like C and make sort of like a comparison of the average of C to some threshold. Okay. This could be a threshold based on some past survey, or it could be last year's threshold, so on. In those circumstances, you conduct a one sample t-test. Here's how it works then. You set up an HO where mu is equal to some test value, and H1 where mu is not equal to test value. Determine the t-statistic, compute the p-value, compare p to alpha. If p is less than alpha, reject HO. Let's look, using our example, let's do a simple test. Is rating of food at McDonald's different from 3? This is a really super awkward research question, but let's just work with it as a simple starter. I'm heading over now to our data set. Again, remember we had a variable called McDonald's there. We're going to examine whether the rating of food at McDonald's is different from 3. Okay. Before we go any further, let me go right back to our data set here and write out here what our different hypotheses are. So our hypothesis is, trying writing right out here. HO is going to be rating of McDonald's equal to 3 versus what? Versus rating McDonald's is not equal to 3. I'm going to switch screens here, switch software here, because typing in is going to be a little hard in the slides. Rather, it'd be hard to do in a PDF. I'm going to switch to a slide view here in just a minute, coming up. Bear with me here. So here we are on a slide view. It'll be easier to view the edits I make in this view. All right, so let's talk about a hypothesis here. A hypothesis is going to be, in this case, H will be rating of McDonald's is equal to 3 versus rating of McDonald's is not equal to 3. Okay, now that we've stated the hypothesis, we have assumed a certain alpha level. Let's go with the default alpha of 0.05. Now we can proceed to examining the data. Here we are, looking at the column for McDonald's now. Sorry. For some reason, I've got a white strip in my view. I'm not seeing this. Things go away. So there. All right, so let's take a look at how you would examine a McDonald's variable. So we want to conduct here a one sample t-test to compare the average of McDonald's to that of some threshold value of 3. So I'll go to compare means, one sample t-test in SPSS, and from there, I will set first a test value. Our test value is, in this case, 3. We want to compare the rating McDonald's to 3. So having set it all up now, we are going to hit OK. Let me hop over to the output window now. Here's our average. Our average is 3.49. We have the standard deviation available with us. We have standard error of mean available from us. So standard deviation is used to compute the standard error of mean. And if you take these two numbers, the mean and standard error of mean, you can compute from that the t-statistic using a simple arithmetic formula. We have 2,000 observations, leaving us with 199 degrees of freedom. 1 degree of freedom used for the mean. So this then translates to a p-value of 0.001 or thereabouts. The number is actually pretty close to 0, but not quite there. So the number is, again, it's less than 0.001, really, really small number. I'm focusing specifically on the two-sided p-value here, and I want you generally as a practice with SPSS, the latest version, not to look at the one-sided p-value. It can be misleading. When we want to compute a one-sided p-value, we will compute that. Don't look at the number on your screen. Rely on the two-sided p-value, and from that, we'll translate it into a one-sided p-value if the need arises. Okay. Our p-value here is so small that it is not even being shown to us because it's less than 0.001. So it's safe to assume then that the p-value is in fact less than 0.05. Let's go back to our slide then. Therefore, since p-value is less than 0.05, it is safe to say then that rating of McDonald's is 3. Yes, you're probably wondering, well, that's a trivial result. And we'll find one that's more meaningful in the next slide. We're now going to move on to another example. Here, we're going to set the question as being, is rating food at McDonald's more than 3.5? Null hypothesis then becomes rating McDonald's is less than equal to 3.5. And H1 is more than 3.5. In case you're wondering how I figured out what is H2 and H1, remember H1, as odd as that might sound, H1 is what you want. So we're hoping to reject the null hypothesis in favor of H1. our our research goal or our goal, or what we are the result we're typically hoping for is in H1, which is why some people disparagingly call the HO a straw man, because we're trying to knock the straw man down in order that we can establish what we're really hoping to find in our data. This hypothesis is one-sided because we are stating here the direction. Specifically, our concern is not whether the rating is below or above 3.5. We are only interested in looking for a rating that is above 3.5. A number below 3.5 would support HO. We're going to go through the same process again of testing, but we are going to get a two-tailed p-value from SPSS, which we're going to convert to a one-tailed p-value to then draw a conclusion about our result. Let me head over to SPSS then. This time I'll stick with the output window. It doesn't matter whether in the output window or the data view, you still have access to the same menus. Analyze, compare means, one sample t-test takes us in there. Here, I'm going to reset. So we have a clean slate. Move McDonald's to the right. And the key point I want to make out here is it's really easy to neglect the test value. The default is 0. That in most cases would not be what you are looking to test. So our test value is now going to be 3.5. That is the only change we're going to make out here. Hit OK. Now, you may have noticed that the statistical steps, or the steps in SPSS for conducting a one-sample t-test and one-sided or one-tailed t-test are the same as those for two-tailed or two-sided t-tests. This is in fact true. Even though we're conducting a different test, or we're conducting a one-sided test here, the steps are the same, which is why somewhere down the road, we're going to convert our result of the p-value to a one-sided p-value. Now, let's go through and examine our result. So first thing to note out here is our mean is 3.49. Now, if you recall, our hypothesis sought to find out if McDonald's rating was more than 3.5. From these numbers, you can tell that our rating of McDonald's in a sample is less than 3.5. We're hoping to find a number for mean that is above 3.5. If we did find a number above 3.5, we would then find out, well, how much bigger is it than 3.5? In this case, the number is below 3.5. So in other words, our mean is not in the direction of the alternative hypothesis. The mean is not in the same direction, or does not support H1. There is no way then we can reject HO. We are going to go further to compute a p-value. So we get a t-statistic from this process and a two-sided p-value. Our two-sided p-value needs to be converted to a one-sided p-value. How you convert it depends on how your hypothesis is set up. The p-value of SPSS is always going to be half of the two-sided. That may or may not be the right thing to do. It depends. It depends on what your hypotheses are. Let's go back to our slide then. So the p-value here is two-tailed p-value came out to be 0.866. I need to convert that p-value to a one-tailed p-value. Before that, I'm going to focus here on the average, 3.49. The average of 3.49 for the sample, that does not support H1, that supports HO. In other words, our sample mean is not in the direction of H1. It is not in the predicted direction. Now, if I want to transform this two-tailed p-value, the formula I'm going to use is the following. 1 minus of 0.866 divided by 2. And that is going to be 1 minus of 0.433, which would be 0.567. I hope I got that right. Maybe some mental math out here. It looks right to me. And that number is in turn more than 0.05. So we cannot conclude rating of food at McDonald's is greater. That's 3.5. Okay. Now, in case this part isn't clear to you, let's go to the next slide where I've got a little cue for you. So if the sample result agrees with H1, you will do what Spss showed you by default and do p divided by 2. If in fact the sample result does not agree with H1, as was the case for us, your math would be 1 minus of p divided by 2. Going back here, 1 minus of 0.866 by 2, 1 minus 0.433 gives us an adjusted p-value or one-tailed or one-sided p-value of 0.567. Okay. You can do a couple of more tests just like this one. Let's do one more before we can go on. So in our case, the next question is health consciousness of people in New Jersey greater than 4, right? So our goal here is health consciousness. NJ. Less than equal to 4. Because our HO will always be the opposite of what we are seeking to establish. We're looking to say or find out that folks in New Jersey are more health conscious than the index of 4. So that's what we'll see in our H1. That's set up now. Now, for this particular test, we have to do two different things. We've got to go through and first filter the data for folks in New Jersey, then compute the health consciousness, and compare that index to the number 4. We're going over to our data view here. And let's see what we have in our data view. In our data view, we have a health 1, health 2, health 3. Our first step here would be to look for location, filter for New Jersey. Second step would be to average health 1, 2, 3 into a health concern or health consciousness index. It turns out we already did that before, so we have a health index already available to us. We'll be using that one, okay? So we're going to then go on to our first step. Second step's already done for us. Select cases for New Jersey. If conditions satisfied, we'll specify here the location as being New Jersey. Now that's tempting to do. I'm almost tempted to say New Jersey out here, but I got to remember here that in our data, New Jersey is coded as a number 4. How do I know that? Let's go back and find out. If I click on the variable view link, this number here will become, or that New Jersey will become 4. To recall, the value labels contains the mapping of the coding to the label. That number is 4. Okay. So back to data select cases, we'll set if condition out here for New Jersey or location to be 4. And then we have only data available now on New Jersey. You can verify that, see that location is only New Jersey. Next, we'll go into our compare means, one sample t-test for reset first and do this for health index. We're comparing this to the value of 4. That's okay. Right, so in our output window, we have a result for us, which is reflecting that the average for New Jersey is 2.79. Let's make sense of this thing. So the average is 2.79 for my state of New Jersey. And let's see what that means. The average is 2.79. So before I even proceed forward to look at the t-statistic or p-value, I'm going to look at this number and see, does it support H1? 2.79. Nah, we don't support H1 with this 2.79 number. Clearly 2.79 is under 4, so it doesn't support H1. So now you got to bear in mind the adjustment you're going to be doing to the p-value you get out of SPSS is going to be based on doing 1 minus p divided by 2. Let's go on further then, pull up the t-statistic and then the p-value. Our t-statistic here is minus 13.344. The corresponding two-sided p-value is 0.001. So our two-sided p-value is approximately 0.001. I'm going to say just leave it at that. I know it's below 0.001, but let's just leave it at 0.001 for right now. And so the one tail would be 1 minus of 0.001 divided by 2, and that would be some number like a really small number, right? This number is going to be approximately, is there a symbol for approximately 1? Would be approximately 1. In other words, this is of course clearly bigger than 0.05. Conclusion, people in New Jersey are not health conscious. I know it's a broad statement I'm making out here. So sometimes, frequently, when you're reporting the results of your analysis, you want to convert that or translate that into a form that people can understand. So I'm kind of overreaching out here beyond the hypothesis here, but you see this happening a lot. So people in New Jersey are not health conscious. And you see a small asterisk, something that's saying health conscious index is so here we have kind of made a statement out here that we are looking at the numbers, and then we have assumed out here that 4 is some sort of a threshold for health consciousness, and we're finding that for New Jersey the number is not above 4, therefore they're not that health conscious. Okay. Right, so far what we've done is in our analysis, we have looked at a given variable, compared that to a threshold or index. Now, there are 2 other comparisons we can look at here. The next one is going to involve comparing groups. You may have frequently got data where you have 2 groups to compare. Just realized that I wasn't sharing my screen. In the wrong screen. Okay, let me quickly review this part one more time because I just realized I wasn't sharing the screen before. So what we found out before was that 2.79 was our average. So, and that does not support H1, and therefore we convert a 2-tailed value to a 1-tailed p-value by doing 1 minus of the approximately 0.001 result we got divided by 2, which is approximately 1, clearly more than 0.05. And that led us to the following conclusion. Our next step then is going to be to go on to our next test out here. Our next analysis is going to be to compare different groups. The previous example looked at comparing a given variable to some threshold number. We're going to move on now and compare two different groups. So here's a toy example that clarifies what we're trying to do here. So imagine now you've got two variables here, B and C. We examined in the previous example the average of C to some threshold. What if you want to know how does C differ across two levels of a variable like B? So are the people who are high on B, different on variable C than those who are low on B? In other words, what happens if you compare high to low in terms of variable C? Are these numbers here different from these numbers? This is exactly what is called for when you're comparing groups across a variable. The test used for evaluating the differences is called an independent samples t-test. So in an independent samples t-test, the hypotheses look as follows. You're comparing the average for group 1 to average for group 2. This is an example of a two-sided hypothesis. So you're looking to see if group 1 is equal to group 2 or not equal to. Now, it turns out that when conducting independent samples t-test, we'll kind of go along the following steps. Our first step is set up the hypothesis as follows. The second step is to conduct an f-test of sample variance. What we're trying to do here is to compare the variances of the two groups. The reason for this intermediate step is that which formula is used for computing the t-statistic depends on assumption of equality of variance. If the variances of group 1 and group 2 are the same, then one formula is applied. If not, a different formula is put to work. We go on then to look at a F statistic and p-value for a test comparing variances called Levine's test. Then we examine the t-statistic, p-value, and if required, we adjust the p-value and then make a decision. Okay, let's put all of these points to practice. The question we have is, do men and women differ in their rating of food at McDonald's? Our null hypothesis here is going to be rating, so just keep it simple, McDonald's men is equal to McDonald's. So our null hypothesis is that the two R groups are equal in their rating of McDonald's. H1 would then be the opposite, but they're not equal. Having stated the hypothesis now, let's go on and examine our analysis results. Here we are in our data view. We are interested in comparing McDonald's in terms of the two genders, male and female. So analyze, compare means this time we'll go to a different menu option. The option we'll look at is independent samples t-test. When you click on that, a window pops up. You're going to move McDonald's to the right. Our grouping variable is going to be gender. Here we're going to specify the groups for gender. Here again, it's important to be cautious. Our groups are not male-female, rather they are 1 and 2. It turns out Spss has already labeled them as 1 and 2 here, groups 1 and 2. It worked out just well for me, but important again, group 1 and 2 here are the numbers 1 and 2. not the value labels male, female. That's it. I'm going to hit OK. Our output window will contain the results. Here we have it. We have males at 815, females at 115N. And then importantly, we're interested in comparing the averages here. Clearly in our sample, males and females are not equal in their rating of McDonald's. Females like it a bit more than males. Now, before we can conduct a t-test to compare these two numbers, we must examine which formula to use. This part can be a little tricky to figure out. Okay. So ideally speaking, SPSS should have broken this into two tables, one that includes just this information, and another one for the rest of this large table. For whatever reason, they have combined them and they've stuck with us through the last 15 or so versions of SPSS that I've used. So I guess they're not going to change it. Let's get used to it. The first section to look at is whether the variances of the two groups, male and female, are equal or not. You can eyeball the standard deviations and see they don't seem to be equal, but they don't seem to be too far apart either. Just looking at those numbers, 1.968, 1.995, intuitively tells me that the numbers are pretty close together. My sense is the variances are probably equal, but we don't know that because all we have is sample data up here. We need to find out if this difference is statistically significant or not. To compare the variances to see if they're equal or not, we conduct a Levine's test of equality of variances. Levine's test is going to give us a F statistic and a p-value for comparing variances. They're as follows. The F statistic, like a t statistic, can be translated into a p-value. Here, that p-value is 0.46, which happens to be, or is, bigger than 0.05. Okay. What does that mean? Well, that means that if you recall from our slide, HO was equal variances assumed. H1 was equal variances not assumed. Since P is more than 0.05, we're going to go with the equal variances assumed because we cannot reject that hypothesis of equality of variances. This is not the same as our main hypothesis. This is a gatekeeper hypothesis we're doing. Okay, so we're going to assume here the variances are equal and go along this row of the output table now. In terms of where we are, this stage, we are on the step of we're on the step. Okay, so we have done the first step was labeling the hypothesis, conducting the F test, looking at Levine's test. Now we're going to go on to find out, well, which t statistic should we be using for our main hypothesis. My annotations are all gone now, which is fine. It looked pretty messy anyway before. We do note that we are going to go here with equal variances assumed because this p-value is above 0.05. So let's proceed along this top row of the independent samples test table. Here you can locate a t-statistic of -0.858 and a corresponding p-value of 0.391. those are our numbers then. Let me go and report these then in our slide. So here is the T statistic, which comes out to be is minus 0.858. The two-tailed p-value comes out to be 0.391, excuse me. That's that. Conclusion, sorry. This is more than 0.05, which leads us to the conclusion, men and women do not differ in their rating of McDonald's. Okay. So in case, and as we go through these slides, in case you're ever confused about how to do one of these analyses, you can always do a search for the running it in SPSS slide, where you'll be able to find instructions of the click sequence for running analysis like in the slide. Moving along, let's examine if men like Chipotle more than women. Specifically, our H1, I'll start tracing our H1 because it's easier to think about H1 with the research question than HO. So I'll say Chipotle men is greater than Chipotle by women. That's our H1. So HO is going to be the exact opposite of H1. And let me put in a less than equal to sign out here. Let's just go less than and then equal to. Okay, so this is our hypothesis. Now, you should be able to look at this and tell that our hypothesis here is one-sided, not two-sided. The reason is that we're looking to see if men like Chipotle more than women. We're not saying they're equal or not equal. We're saying one is more, one is less than or equal to. So it's one-sided for that reason. Anytime you see a one-sided test, you will have to adjust the two-sided p-value to make it one-sided. You don't want to use a one-sided p-value from Spss because it ignores what our real hypothesis is. Okay, so let's go on and conduct this test, and ultimately we'll have a conclusion. We're done with this. Let's go over to our data view. So here is the variable of interest, Chipotle. We're comparing Chipotle across males and females or men and women. To conduct the test, we could analyze, compare means, independent samples, t-tests. Next, reset this whole thing and move Chipotle over to the right. Set up our grouping variables being gender and the levels being 1 and 2. Having done all this, run the analysis. Our output looks as follows. All right, so let's take a look now. We have here 3.94 and 4.03 for our averages. Let me go and report these first. 3.94 for men, 4.03 for women. Okay. Interesting. Okay, I'm intrigued here because, okay, our H1 is proposing that men like Chipotle more than women, but our sample descriptives are giving us the opposite story. In other words, our sample statistics, sample descriptives do not support H1. So this affects how we're going to adjust our p-value later on in this analysis. Okay. Let's now proceed to compare the variances of males and females using Levine's test, draw a conclusion about variances, and then examine the appropriate t-statistic and appropriate two-tailed p-value. Here's the output then. We are now going to compare the variances by looking at Levine's test below. Levine's test compares the variances of males and females and concludes something. Specifically, it concludes that for the equality variances assumption, which basically amounts to looking at HO here, H1, the p-value is more than 0.05. And because more than 0.05, we're going to go with the equal variances assumed assumption. Because we're going to assume the variances are equal, we're going to proceed along row 1 and only work on row 1. Here we have it then. Our two-sided p-value is 0.234. Oops. Now, what you don't want to do is again look at the one-sided p-value here. Don't look at that. We go back to SPSS now. Go back to our slide. Report the results. Our two-tailed first variances are equally concluded that. And we also find our two-tailed p-value as being, t-statistic as being minus 1.191. Our p-value was 0.234. Let's just go and verify these numbers are correct. Picked up the right numbers. The numbers of interest then are the following: this one here and this one. Okay. Great. So we now need to adjust our p-value. Remember, our sample averages don't support H1, so we must adjust by doing 1 minus of that two-sided p-value divided by 2 equal to 1 minus of 0.117, if I got the math right here, which comes to 0.883, is that right? I'm going to verify this with a calculator. Make a mistake out here. Okay, that's correct. So our adjusted p-value is 0.883, which is more than 0.05. In other words, our conclusion is we cannot reject HO. Okay. So rating of Chipotle by men is less than or equal to rating of Chipotle by women. Or you can go with a simpler result, more meaningful result, that men don't like Chipotle any more than women. All right, so moving along, here's a bit of the math with a toy example of how you do the one-tailed and two-tailed conversions or interpretations. Okay, we can repeat the same kind of analysis for Shake Shack, comparing Shake Shack across locations, comparing Manhattan to other locations. This might actually be worth doing. Let me go in and do this one as well then. So our goal here is to compare the rating of Shake Shack is less than or equal to Shake Shack other locations. And H1 is that it's better, right? So again, the H1 here is that Shake Shack is like more consumers from Manhattan rate Shake Shack higher than other locations. That's what H1 is reflecting. Okay. Let me go and run this out now, run this through. Now, this one is a little bit of a, you got to think about this question a little bit because we have here Shake Shack, and then we have locations. We have 4 locations. You must be wondering, the question is having us compare Manhattan to all other locations. How do you do that? Because when you go to define group in the independent samples t-test, you've got to specify 2 groups, Manhattan and other locations. In other words, we need to group New Jersey, Brooklyn, and Queens into one bucket and Manhattan in the other one. Here's where some of the data prep we did before is going to pay off. You'll recall we created dummy variables for location. We can leverage those dummy variables now. A dummy variable is like a switch. It's either on or off. One of our dummy variables was dummy Manhattan. Here it is. When the location is Manhattan, dummy Manhattan is 1, otherwise it's 0. So we can use dummy Manhattan now for comparing groups. Okay. Analyze, compare means, independent sample t-test. Let's pop support layout. Let's reset everything actually. We'll put Shake Shack in here and compare Shake Shack across not locations, but values of dummy Manhattan. Our groups now are not 1 and 2, the default, but they're 0 and 1. Let's go 1 and 0. Now it doesn't really matter what goes group 1, what is group 2, because we're simply comparing 2 groups. The sign is reflective of what order you compare them in. You compare, 7 to 5 or 5 to 7. Well, 7 minus 5 is plus 2, 5 minus 7 is minus 2. If all you care about is the difference, the absolute difference, it doesn't matter what order you compare them in. Okay. Having run that, here's our result in SPSS. So we have an output window with our respondents. We have here almost 1,000 respondents from Manhattan and approximately equal number from outside Manhattan. The averages are telling us a story here, right? The averages are telling us, yes, indeed, in terms of sample average, consumers from Manhattan like Shake Shack more than those from outside of Manhattan. To figure out what formula to use, we're going to compare the variances using Levine's test of equality variances. And that looks as follows. So this sig value here is above 0.05. The p-value is about 0.05. And therefore, we're going to go with equal variance assumed assumption. Looking along this row, you'll find that the t-statistic is 1.237, and the two-sided p-value is 0.216. Therefore, our p-value we're getting at is 0.216. Let's go over and report some of these numbers in our slide. So the average for Manhattan is 4.03. For not Manhattan is 3.93. Levine's test told us variances are equal, which yielded a t-statistic of 1.237. Two-tailed p-value of 0.216, a one-tailed p-value of what? We don't know. Let's go back and review our sample averages. So our sample result is telling us that Manhattan, Shake Shack in Manhattan is liked more than Shake Shack in other locations. In other words, our sample averages are compliant with H1. They are in the predicted direction. Therefore, in this particular instance, our conversion would be 0.216 divided by 2. Turns out even that halving of the p-value is not helping. It's still about 0.05. Therefore, there is Shake Shack is like the same by p in Manhattan, other locations. Okay. Alrighty. This brings us to our last of the 3 tests we're conducting here. Now we're going to compare different variables. Back to our toy example. Imagine you've got a data set with 2 columns, C and D. C is one variable, D is another variable. We want to compare them. The test to use is a paired samples t-test. The paired samples t-test looks as follows. You compare your goal is to compare the average for one group to the average for another group, if it's two-sided. Once you've set up the hypothesis, next step is t-statistic, p-value, adjust the p-value if required, compare the p-value with alpha, and make a decision to reject HO or not. So let's go on and draw a comparison. Maybe you want to know if the food at McDonald's and Chipotle are different. So our null hypothesis here is McDonald's rating is equal to rating is equal to rating of Chipotle. And each one is the is it they're not equal to? Okay, so let's go and now run the test, compute the averages and so on and so forth. Now, bear in mind, we have here a two-sided test, so no need to adjust the p-value that we get from SPSS. We're off to SPSS now. Our goal here is to compare Chipotle to McDonald's. These 2 columns here. To do this, we'll do analyze. Compare means this time we're going to go to a different menu option. We'll go to paired sample t-test. Here, we're going to move the variables McDonald's and Chipotle. Also, like both simultaneously, using either control on a Windows machine or command on a Mac, or you can use shift since they're consecutive. Then bump them over to the right, and that's all there's to do. Hit OK. The output window contains our result. Looks as follows. So we have here the average for McDonald's is 3.49, for Chipotle is 3.99. The difference is minus 0.502 after accounting for rounding. And importantly, the corresponding t-statistic is 8.475, or other minus 8.475. And the two-sided p-value is less than 0.001. Let's go and look at this then. So McDonald's rating was 3.49, Chipotle was 3.99. statistic came to be minus 8.475. As was the case for a independent sample C test, the sign is not as that relevant out here because we're really comparing difference. We're focused on the difference, not the direction of difference, because we already know what that direction is. The two-tailed p-value is going to be less is equal to less than 0.001. Conclusion, which clearly is less than 0.05. So I'll just put that in here too. Are different. Moving along, let's take a look at one more example. Here, our goal is to compare the rating of food at McDonald's and Chipotle across 18 to 29-year-olds. Okay. Actually, let's get past this one to one that has a one-tailed test. So we're going to look at a contrast of Chipotle to Shake Shack for people living in Manhattan. Specifically, the question is asking in Manhattan, if in Manhattan, Chipotle is rated higher than Shake Shack. So here we have it. We have the research question expressed in hypothesis form. In Manhattan, rating of Chipotle is more than that of Shake Shack. That's our H1. H2 is the opposite of that. As you can tell from looking at this pair of hypotheses, this is a one-sided or one-tailed hypothesis. Let's go and run the test now. Pop over to SPSS. We're comparing Chipotle to Shake Shack, but only for folks living in Manhattan. So let's first begin by filtering a location. Location Manhattan is 1, so we'll go to data, select cases. Here we're going to specify a filter of location is equal to, we'll specify filter 1. Hit OK. And next, we're going to run our test, analyze, compare means, compare sample C test. Here we're going to compare Chipotle and Shake Shack. I'll select both simultaneously and bump them over to the right and hit OK. Our result is as follows. We have here Chipotle and Shake Shack showing up in this window. Chipotle 3.9, Shake Shack 4.03. You can tell out here Shake Shack is liked more than Chipotle. So let's see what that difference is. The difference is minus 0.123. The corresponding t-statistic is minus 1.532. And the corresponding p-value is 0.126. Let's put these numbers together. So Chipotle is 3.9. Shake Shack is 4.03. The t-statistic is minus 1.532. And the two-tailed p-value is 0.126. To adjust the p-value, to do that, let's examine our averages. So each one indicates that Chipotle is more than Shake Shack. Our sample averages indicate the opposite. So our result is not in the predicted direction, and therefore adjustment would be 1 minus of 0.126 divided by 2, which would bring us to, let's do this, 1 minus of looks like 0.063. That should be 0.937. I'm going to run this in the calculator to be sure about the numbers. Okay, those are fine. That's the p-value is therefore more than 0.05. Conclusion is Chipotle any more than Shake Shack. People living in Manhattan. Okay, that is our final conclusion then. To wrap up proceedings out here, or before we can do that, let me just quickly highlight a few more tests you could potentially conduct out here. You could also conduct non-parametric tests. This involves comparing groups where you don't make assumptions about the underlying distribution of the data. And you can do those comparisons as follows. If you have typically there are these independent samples analog and paired samples analog for non-parametric tests. You can find these in Spss. I'll show you where in just a second. You have alternative tests involved for conducting these analyses, like Man, Whitney, U, and so on. And setup is very similar to that for independence for parametric tests, but the interpretation is a little bit more challenging. So if you had to run this in Spss, you would basically go over to analyze non-parametric test legacy dialogues. Here you can look for 2 independent samples, and here you plug in the information that you want to compare. If your interest was going to compare men and women in terms of McDonald's, you'd do the following, and that's it. You plug in these values here, 1, 2, and you hit OK. Similarly, to do a paired comparison test using non-parametric statistics, you would do something very similar. You would, let's say you want to compare McDonald's and Chipotle, see if they're different or not, based on, without assuming assumptions about the underlying distribution. You'd go over to Spss again and analyze non-parametric tests, legacy dialogues, paired samples, 2 related samples, and then you would move Chipotle and McDonald's over. And hit OK, right? Okay, so to wrap up then, we've examined in this session descriptive statistics. We also examined inferential statistics and hypothesis testing. Specifically, we examined how to compare a variable to a threshold, compare 2 groups, and compare 2 variables. Thank you for joining me.